This is the second video for, let me find it, March 6th and March 9th. We're looking at the graphs of rationals. We spent some time solving rational equations, and now we want to look at the graph of the rationals. So when we talked about this in class, we talked about key features that make this function unique. And initially what we noticed is we have two sections of the graph. So we have like this section here. It's not a parabola. It's not that U shape. But we do have a section of the graph here. We have a section of the graph here. This dot is an x-intercept, nothing special here. But here we have an open circle, which means the function doesn't touch this value. I should probably make that like more of an open circle. There's that value. We have these two dotted lines. We're trying to figure out what those are telling us. Let's start with the dotted lines. So these dotted lines, we talked about similar to what we had when we looked at the graphs of tangent, secant, and cosecant. And when we graph those, we said those are undefined lines, which is true. But those undefined lines have a specific name to them, and they're called asymptotes. And so what we can say about this function, I'm going to write it down here. Hopefully we can have enough room. For this function, f of x, it has two asymptotes. We'll start with this asymptote. So if it's a straight line going straight up and down, we would say it has a vertical asymptote. So f of x has a vertical asymptote. At, and we want to figure out the equation for this line here. Well, it touches here at x equals 2, and that's the exact equation of the line. Because if you think about it, this ordered pair, the ordered pair at this point would be 2, 5. The ordered pair at this point would be 2, negative 3. So x equals 2 this entire time. So we have a vertical asymptote at the line x equals 2. F of x also has another type of asymptote. Here, if it's straight like this, we call that a horizontal line. So we have a horizontal asymptote. Horizontal asymptote at the line here, y equals 1. It equals 1 the entire time on that dotted line. So we say it has a horizontal asymptote at the line y equals 1. Now, a few things. The vertical asymptote, we're going to be able to describe why that's happening. The horizontal, come back next class, maybe watch the next video if you weren't in class to determine where that horizontal asymptote is coming from. But we can determine vertical, and we're going to do that. In class, when we talked about this function, we looked at this fraction, we noticed that we have a quadratic here and a quadratic there. So what we decided to do is factor our quadratic functions. So if we look at our numerator here, we can factor that as x minus 3, x minus 1. Our denominator here would be x minus 3, x minus 2. Now from here, people notice, we can't divide by 0. So we do a similar thing when we solve our equations. We say here that x cannot equal 2, because if x equals 2 here, we have 0. 0 times negative 1 would be 0, so we can't have that. Also, x cannot equal 3. Now this is interesting, because if you look at what x cannot equal, when we look at our graph, at x equals 2, here, 1, 2, man, that's where our asymptote is. That's where our function cannot touch. Well, this part cannot get there. This part cannot get to 2. So we have a vertical asymptote there. Here at x equals 3, 1, 2, 3, we have a hole, meaning our function gets close to 3 but never touches at 3. So we're trying to figure out like what's happening here. Why do we have an asymptote at 2 and a hole at 3 and not, and vice versa? Why do we have a hole here and not a hole here? And what we talked about in class is here, the x minus 3s, we have to pause. We have to originally look at our original function. Great word choice. But if we look at our original function, then we know that x can't equal these two values. But now if we look here, the x minus 3's, those go away. And we're left with x minus 1 over x minus 2. So if you notice, the x minus 3 went away when we divided things out, but the x minus 2 stayed. So if a value that x cannot equal stays, this cannot equal 2, this stayed with our function after we simplified. If it stays, then we will have an asymptote, a vertical asymptote. If we can remove what x cannot equal, here we remove the 3, the x minus 3, then what we say is f of x, can you see that? Yep, has a hole at the value x equals 3. So one more time, if the value stays, here the x minus 2 stayed. If it stays, then x still can't equal 2, and that's going to give us a vertical asymptote. However, if we can cancel it out, if it goes away like the 3 did, then we say x still can't equal 3. It still can't equal 3. However, we have a hole at 3. We have a hole at 3, not an asymptote. We're going to get better at recognizing these in the future. Now, a few other things really quick. If we want to talk about domain, this is something that I would ask for on the assessment. Range can be a little tricky with these functions, so I'm not going to ask for range. But when we talk about domain, no longer can we take all values. We can't say, again, domain, we're talking about the x-axis. From negative infinity to infinity, we can't take all the values, but we can take almost all of them. So we can say the function can take all real numbers, and I would take this answer on assessment. But you can take every single real number except for here at 2 and 3, or essentially what's happening here. But x cannot equal 2, x cannot equal 3. So our domain is similar to what it's been in the past, but it can't take 2, it cannot take 3. Also, I probably wouldn't ask for this, but it's good to recognize. If we wanted to talk about end behavior, as x goes to infinity, as x goes to negative infinity, we could do that. I'm going to say f of x approaches. F of x approaches. We can talk about end behavior now. And what's happening here is x goes to infinity. As we keep going forever to the right, what this function is doing is it's going down, 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 and then it flattens out, and it doesn't continue going down forever. What's happening is this function is going to get really, 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 really close to this value at 1, but never touches. So what we say is this function, as x goes to infinity, as we keep going to the right, this function is going to eventually approach but never touch the value at 1. Similar thing in the negative direction. If x goes forever in the left-hand direction, this function goes up, 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 but then it flattens out, and it never touches 1. It never actually meets at 1, but it approaches 1. So we have new end behaviors here. If you have questions about this, hold on to them, bring them to me in class. We're also going to go over this in the next class as well. I'm going to go and flip to the back page quickly. Here we have multiple asymptotes. For this function, I would encourage you to try to explain why these occur. Not the horizontal. We would have a horizontal asymptote here at y equals 1. We'd have 2 vertical ones. Here at x equals 2. And here at x equals negative 2. I would encourage you to try to describe why do we have these 2 vertical asymptotes at x equals 2, looking at this function. And here, this function here, x squared minus 2x, we actually have, or x cubed minus 2x over 2x squared minus 10. Here we have 2 vertical asymptotes. And we don't have a horizontal asymptote, we have a slant asymptote. Slant asymptote. And we're going to see next class on why those things occur. But if you want to try to figure out where these vertical asymptotes occur, go for it, see if you're right by asking me in class. And definition, I'm gonna leave that there. If you really want the definition of an asymptote, ask a friend, come talk to me in class. I'm gonna cut the video here for time though, but we'll have plenty of time to talk about these functions over the next couple of classes.